name is Prayush Kumar. I'm going to change the course just a little bit and talk on a different aspect of GR, and that would be numerical relativity and how it has been contemporarily applied to an interesting problem, which is that of black hole mergers. What are the challenges that we have faced, and some of them we have overcome, many of them we still have to overcome. So I'll summarize all of that. So to start with, I am stealing a figure from Anupreeta's talk where we show some of the black holes that we have seen in the gravitational wave spectrum with the LIGO-Virgo detectors in the recent past. So here, as you go up, is the mass of the black hole, and see these are all hopefully mostly stellar collapse black holes. And above this horizontal white line that I've drawn here is pretty much the population of black holes that merge at low enough frequencies such that LIGO is mostly able to see the last few orbits before these black holes merge and form a single Kerr black hole, right? And that means that for these black holes to be seen, information in the truly strong field gravitational regime is required, and numerical relativity is sort of the only way to get access to that information. Some of the lower mass black holes here spend a lot more time in the weak field region within the sensitivity band of LIGO-Virgo detectors. So they require less of, we can both detect and analyze them using usual perturbative methods like post-Newtonian theory, etc. So just a very, very brief recap. So these binaries that I'm talking about, they spiral along on quasi-circular orbits, tightening the orbit by the emission of gravitational waves and loss of energy through these waves. Ultimately, they merge to form a single distorted black hole, a single distorted horizon that looks like this. This is a snapshot from an actual numerical simulation, and which then sheds away its anisotropies to form a Kerr black hole. And this also is a snapshot from a numerical simulation that for two black hole merging system. So numerical simulations are, in fact, we found that they're necessary for binary black hole science. Why? Again, remember the first slide. We have an unexpectedly large number of rather massive black hole mergers that we are seeing. And so in order to do justice to most of these events that we see in the gravitational wave spectrum, we need information in the truly strong field regime of the process. In fact, without using results from numerical relativity, more than half of all the events that have been seen in the spectrum would have been detected with much lesser significance, and certainly their masses and spins and all other interesting astrophysical properties would not have been measured with nearly as much accuracy as they have been so far. In fact, we would not be able to test GR in the really strong field regime just as well or nearly as well as we have. For example, one of the tests that we do to look for violations of GR is we try to measure the mass of the final black hole from the pre-merger portion of the signal and compare it from an independent measurement from the post-merger part of the signal, right? And if we don't use information from numerical relativity, the two measurements actually would be this ambiguous as these dashed contours shown here. Whereas when we include information from NR, we measure these same masses and spins on the final black hole much more precisely. So this is just an illustration, in fact, using the very first gravitational wave event that we saw in 2015. Okay, so before going into more detail, let me quickly show an animation, a movie of one of the more popular simulations that we have done in the recent past. So this. Okay, just bear with me for a second. Right, so what is shown here is the inspiral of two black holes. In the outer region, the colors show the gravitational waves being emitted. In the inner region, the color shows the time dilation, red being more. And this plane, of course, is the orbital plane of the binary. And the height of the plane here gives the amount of spatial curvature that we have. So you can see the curvature is maximum near the two black holes. And you can also see the plane of the orbit changing in orientation. And that is because of the intrinsic spins of these black holes coupling with the orbital angular momentum to sort of give rise to a precession of this orbital plane. And the movie slows down as we come to the final few milliseconds before merger. And this is, for example, the moment of merger where we for the first time, see the appearance of a common apparent horizon. And not long after, that apparent horizon settles down into a Kerr black hole state. So this again, this comes from a real numerical simulation, and the corresponding waveform is shown at the bottom here. And this actually was the first event that we saw in 2015 again, GW15 or 914. Okay. 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 So I'm going to skip over this and move on in the interest of time. So let's get into a little bit of details of how we do numerical relativity. As you probably understand, the goal here is to calculate the dynamical space-time metric, the metric that determines the geometry of our space-time, as it is affected by the presence of matter and momentum and other flows in the space-time. And this is done by solving Einstein's equations, which are a set of coupled second-order nonlinear partial differential equations in about 10 independent variables. So this problem was first attempted to be solved on computers in 1964 by Susan Hahn and Richard Lindquist, where they were able to do about 50 small time steps into the evolution of a binary black hole system before their code crashed. It ran into floating point errors. And it took around 4 decades for the very first stable simulations to appear in literature. And we'll talk about why. So there were profound difficulties that had to be overcome in these 4 decades. So this is the paper that showed the first few orbits of an equal mass binary black hole system and the associated gravitational wave emitted by that system. Soon thereafter, other groups in the world also were able to follow suit and perform stable evolutions of binary black hole systems. So how do we actually go about solving Einstein's equations? So now typically, because we are human, what we have access to is the state of a astrophysical system at a given value of time. So it is natural to sort of split the 4-dimensional Einstein's equations into split space-time into space and time separately. And through that split, what we find that these Einstein equations result into 2 different set of equations. First is a class of evolution equations, which given the state of the system at some time, initial time here, can be used to evolve to some time in the future. Also, we get a set of coupled elliptic partial differential equations in the form of constraints, which constrain the geometry of the physical state on each of these slices independently. Right? So this is not unlike Maxwell's equations, which, if you think about it, the first 2 are equivalent to the evolution equations that I've talked about, and the last 2 here are similar to the constraint equations that we have. Okay, so what exactly makes numerical relativity challenging? What makes these simulations hard? So there's a bunch of different things. The most important currently is the fact that we have many length scales to resolve in this problem, right? Starting from the size of the black holes to the separation of the black holes to the wavelength of the gravitational waves being emitted by the inspiral of these black holes, and also the fact that we have to let the gravitational wave propagate out for some distance before we are able to measure them unambiguously. So that brings about 4 orders of magnitude of different length scales into the picture, which we have to resolve simultaneously at all times during these simulations, right? Then, of course, with the length scales come different time scales, right? Because the smallest black holes is horizon is showing dynamical properties at the smallest of time scales as compared to far away from the source, where we have nothing but simply the gravitational waves propagating on much longer time scales, right? So the next important point to consider is we don't know what coordinates to use a priori, right? We're going to put a singularity on a computer grid. We better take care of our coordinates, and the problem is, before doing an evolution, we don't know which coordinates necessarily will be amenable to that simulation. And so this takes a bit of iterative learning to understand which coordinates would be better than others, right? Then actually handling the singularity on the grid is in itself a complex problem, which different groups around the world, they handle differently. And then we have this point 4, which actually was the key difficulty that took the longest to be sort of conquered, which is the fact that when we start from some initial state of the system and start evolving using the evolution equations, even though initially the constraint equations were satisfied, what we find is numerical errors creep into our simulations very, very quickly, in fact, and they grow exponentially with time, so as to destroy the simulation. And these have to be handled quite carefully and made sure that we sort of have inbuilt in our methodology a way to damp away any violations to these constraints. Okay, so then resolving shocks is always fun. This is not so much a problem with black hole systems because space-time metric field is smooth. But when we have neutron stars and black holes, or just two neutron stars into the as a system that we are evolving, then they certainly form shocks, especially at the moment of contact. And being able to resolve them is in fully relativistic regime requires some careful maneuvering of the control systems involved. Next, of course, are the computational challenges of solving Einstein's equations. So depending on whether you're solving a second order form or a first order reduced form, we can easily have from 20 to up to 50 variables to simultaneously evolve. And also the global time step here can also be quite small. So using global time stepping is a major handicap that we still, the current generation of NR code still have. And that's the bottleneck currently for all of them. And last but not the least, the accuracy requirement for applying these simulations to analyze gravitational wave events is quite high. In fact, we need phase accuracy much, much smaller than a radian for every, say, 20 to 30 orbits of simulations, right? So some of these challenges can be overcome, for example, at least the last two, by realizing that in vacuum, solutions are smooth. So we can go ahead and use spectral methods, which is a nice segue to introduce the spectral Einstein code, the code that I've been a part of developing and using. So this has been developed as a collaborative effort by the Simulations of Extreme Spacetimes Collaboration. And this is spread all over the world. Several continents are involved in this effort. Originally, this was started as a collaboration between Caltech and Cornell, which has now flourished everywhere. So, right. So the spectral part of spectral Einstein code is due to the fact that we use spectral discretization instead of a finite difference of finite volume kind of discretization. And very briefly, what this means is that if you have a field that you want to solve for, you decompose that field into a set of basis functions. And that separates out the time and spatial dependence of that field, which means that we are able to get the spatial derivatives. One of the advantages is we are able to get the spatial derivatives of that variable without any additional approximation. Okay, thank you. So we are able to perform spatial derivatives of any fields almost exactly, because the derivative operator operates on the basis function, and all time dependence is outside of it, right? So now going back to the goals of, going back to the challenges, let's look at how spec addresses, or at least tries to address some of them. So the first one I've talked about was the question of handling multiple length and time scales. And the way we get around them is by using adaptive meshes. Adaptive meshes adapt to the length scales and time scales of the problem locally. So in all the regions where smaller length scales exist, smaller time scales exist, adaptive meshes will automatically refine themselves. And where we have large length scales, for example, simply waves propagating outward, these meshes will again unrefine themselves to sort of optimize the efficiency of the simulation per grid point, right, per unit volume of computing. Now, which coordinates to use? We use a variation of harmonic coordinates called generalized harmonic coordinates. Harmonic coordinates are the ones that have been used in analytical relativity for a long time. They particularly are suitable for reducing Einstein's equations to a nice wave equation-like form. And the generalization of them turns out to be quite a stable gauge to use when performing numerical simulations. Now, when we put black holes on a grid, what spec does is it takes a small region of space-time which is outside the singularity yet inside the horizon, and it excises that region from the grid. So it doesn't place any grid point within that small region. So in other words, the singularity is sort of, rather the grid is sort of protected from the singularity through this excision. Then the most important development that happened around 2005 and between 2005 and 7 was how to make sure that Einstein constraints were actually not being violated during these simulations. And in order to do that, the generalized harmonic form of Einstein's equations, we had to modify it to add certain terms that are proportional to these constraints, such that when you rewrite the evolution equations, when you rewrite the evolution system for the constraint equations, you find that they have an exponentially damped behavior. Okay? So now resolving shocks, again, as with any code that uses spectral methods, the spectral grid in itself is unable to resolve shocks. So what do? We have two overlapping grids, one which does finite difference in the regions of space-time where there are shocks likely to form or are already forming, and everywhere else we use a spectral grid, and the two grids communicate at every time step to sort of one of them is evolving matter fields, one of them is evolving space-time fields, and so at every time step they communicate and exchange information about the variables that they are respectively evolving, right? And then last two I've already talked about. So let's really quickly look at some of the results that spec has produced over the years. So in 2007, this was the first stable simulation performed for an equal mass binary black hole in spiral merger, where the two black holes did not have any spin of their own. And this was stable enough, thanks to spectral methods, that people were able to evolve around 15 orbits. And you can see the constraint violations here as a function of time on a log y scale. You can see that they were quite well controlled. And this is the moment of merger of the two black holes. And you can see the constraints increase near that moment. Still, they remain quite well bounded. Okay? And from there, a few years later, in 2013, we released the first catalog of about 170 simulations. Each figure here shows the waveform coming from one of these simulations. And they were the first set of waveforms that were made open for public use. And so this, like 2 years later, came the first gravitational wave event that we saw, GW150914, and this is yet another animation from the same numerical simulation that I showed you earlier, from a slightly different point of view. So let me quickly try to play this, and that's not the one. Okay. So the okay. Somehow it's playing on my screen and not the other screen. Okay, so we have a system of nearly equal mass black holes sitting at the center here.
16 for up to 16 free meals and 3 surprise gifts. This is a great company, and the cherry on top is that they're also carbon neutral.
Near the
a big
source,
thanks to HelloFresh for supporting educational content on YouTube.
I think there's a separate tab open. Okay, so outside here we see the gravitational waves being emitted by the system, and in there was the strength of gravitational field near the black holes being depicted in red to green colors. And this is the moment of merger, and after that, if we zoom into the picture, we see a curved black hole sitting right there. Again, this the SXS collaboration is responsible for the simulation and the visualization being shown here. Okay, sorry about this. Every time I exit this, it rewinds my slides. Okay, so the same year, the same simulation was actually part of the detection publication, where you can see in this figure that is taken from the same paper, from written by the entire LIGO-Virgo collaboration, the raw data filtered from the Hanford and Livingston observatories, and a SXS numerical simulation overlaying the time gap, the timestamps. Okay, so about a year later, we published another set of 95 high mass ratio binary black hole simulations, where all the black holes involved here had moderate to high spin angular momentum on them. And not so long after, a massive effort, a massive campaign was undertaken to perform a large set of these binary black hole simulations that were all made public in 2018, a cumulative total of about 1,000 of these simulations. And you can see how long these simulations were, so via this histogram. So most of them were about 40 orbits long, with some of them being much longer, and these simulations were performed with explicit intention to make comparisons with perturbation theory, like post-Newtonian theory's results, and so as to have some overlap between the domain of validity of Poisson theory and the numerical simulations. Okay, so another update was released to this catalog the year after, where another set of 1,000 simulations were again released, bringing the cumulative number of simulations that we have so far to about 2,000. And because it's hard to summarize this many simulations, this figure here shows sort of the distribution of the parameters of the binary that these simulations have been evolving. So you can see mass ratio Q here, and versus spin of the smaller black hole, spin of the bigger black hole here. And you can see most of the simulations lie between mass ratios of 1 and 5, and several of them lie between mass ratio 5 and 10, with this line standing out corresponding to a set of non-spinning simulations, right? Okay, so 2 years later, we started to follow up the incoming gravitational wave events that were being seen every few months by LIGO and Virgo detectors. And this movie is supposed to show us a set of simulations that were made to follow up the events seen between O1 and O3, the first 3 observing runs of the LIGO-Virgo detectors. Okay. So you can, okay, that went by too fast. I think the movie is going to repeat all of them. So notice that all of these events are different mass ratios. For example, this one. Some of them are comparable mass ratios, and they all merge at the same time in this movie. And so these are simulations that were run to follow up specifically the events that LIGO and Virgo detectors have been observing so far. Okay? Okay. Let me quickly zoom by. Okay, so some of the technical accomplishments that we have made, for example, the first one is being able to perform long, stable simulations. So I really want to highlight this one, which was mass ratio 7 system, which did not have spins on the black holes, but it was stably run for about 180 orbits. In fact, it is one of the very, very few numerical simulations that cannot be resolved on a PowerPoint slide, right? Usually these simulations are much shorter. Okay, and when we say stably evolve these systems, we mean while maintaining excellent phase tracking, excellent accuracy in terms of the orbital dynamics and the emitted gravitational waves. Also, the accuracy of doing these simulations accuracy has gone up, but the cost of doing these simulations has gone down quite a bit. So it used to be around 100,000 CPU hours back in 2007 for a simulation of only 20 orbits. It has gone down to up to, say, only 20,000 CPU hours as of the moment, I think 2 years ago, when we were able to last measure this cost on a large scale. Right? And the cost really depends on how accurate you want the simulation to be. And as you can imagine, so look at the number of grid points as a function of physical time in that simulation. So this is during the in spiral, where different resolutions, they're running at fairly constant number of grid points. This requirement shoots up near merger, and then again goes down. So naturally, as you can imagine, as the dynamical system, as the two black holes get closer, as more of the strong field dynamics needs to be resolved, we need more points, and therefore the simulation becomes more and more expensive. So broadly speaking, how are these waveforms being applied to gravitational wave astronomy? So the most fundamental way through which these simulations help recover information from real signals is via waveform models. So there are semi-analytic, semi-phenomenological waveform models that we use in all aspects of gravitational astronomy, starting from detecting these gravitational wave signals in low latency, in high latency, then assigning statistical significances to them, understanding their properties, their astrophysical origin, everything. They all require a good understanding of what the underlying signal would look like, right? And numerical relativity has been instrumental in exactly that, ranging from non-spinning binary black hole models to models that include black hole spins, but these spins are aligned to the orbital angular momentum, to waveform models which allow for misaligned black hole spins and angular momentum, leading to a precession of the orbital plane. Also an amplitude variation of the gravitational waves being emitted, so the spin precessing models, and also to eccentric orbits, so to binary black holes that are formed in dynamical sort of situations, close encounters, etc. So numerical simulations have informed models in all these regimes. We can even do parameter estimation on very high mass BBH events using numerical simulations directly. So for example, these two figures show the measurement of the final black hole's mass and spin for two different events from 2015 and 17. And the sort of the green contour here and here tells us the constraint that we can put using NR data alone, while all the other contours correspond to different waveform models, right? So we can, if we wanted, we don't do this yet, but if we wanted, we could actually search for binary black holes in gravitational wave data using NR data alone. So here, for example, I'm showing results from the suitability of a search with NR simulations alone, and we can certainly detect all events which have a total mass of 40 solar masses or higher, and spins on the two black holes of up to plus 0.7-ish or so, right? And just to illustrate what's important about this region, most of the events, well, not most, more than half the events that we have seen actually lie in this very corner of the binary black hole parameter space, including some illustrious events that I've explicitly shown here. Now, we've already talked about this. We use information from NR to test general relativity. Now, okay, so in the interest of time, I want to move to the second half of my talk, where we want to look at where we go from here. These were the goals I talked about. These were the difficulties or challenges I talked about earlier that faces any person who wants to do a full numerical simulation of with Einstein's equations. Some of these, which are now grayed out, have been quite reliably addressed, the challenges. For example, the choice of coordinates to use, handling singularities and constraints. They have been all, we have a good control on all of them. What we don't have yet a good control over is, and by we, I don't mean simply the SXS collaboration, I mean these are limitations of pretty much all the current generation numerical codes across the globe at the moment. We have some ways of addressing these residual points, but they definitely need a lot more improvement. So the first is the ability to handle multiple time scales. So you can see from this picture here that the smallest length scales and time scales, they exist in this region near the source here, while outside is pretty much empty space, right? And so the one in principle could use a different time step. Instead of having a global time step evolving the system all synchronously, one could evolve much slower near these black holes and much faster far away from the black holes in the empty space, and save a lot of, rather make these simulations far more efficient. Remember, they still cost 20,000 CPU hours per simulation, right? So this would be something to conquer. Next is being able to resolve discontinuities without sort of having to resort to rather expensive methods, or being able to resolve discontinuities while maintaining higher than second order accuracy is something that has not been yet achieved. And of course, being able to run these simulations faster and in a way that makes optimum use of future computing. So as you would have noticed, in the last decade, our computers individually, the computing cores, have stopped sort of becoming faster over at least the last 10 years. What we have been able to do is pack more and more cores onto a single chip, and that changes the nature of our endeavor, right? Because we can no longer write something that is not trivially parallelizable, because the future, when we go towards exascale computing or even higher, what we will have is millions of cores lying around, but an individual core may not necessarily be significantly faster than what we currently have, right? So we need a much more robust way of dealing with these last couple of points, which are actually coupled together. Okay, so we went back to the drawing board and took up these as the challenges to sort of overcome, and we realized that all four of them can be overcome by making three key paradigm changes. First, is the way we look at, the way we discretize Einstein equations and MHD equations, etc. That needs to change. All the codes use finite difference, finite volume methods or spectral methods. We find that neither of them are quite suitable because they all require a lot of communication the moment you want higher order accuracy, which is why all of our simulations with neutron stars are only second order accurate, which is terrible, right? So the next paradigm change that we want to make is a different way of parallelizing all the calculations, and we'll talk about that in time. And also the local time stepping, the paradigm that I had already talked about, being able to take small time steps near the regions where you have small time scales and large time steps where you have larger time scales would be extremely handy, especially when we are trying to evolve a very high mass ratio system, say 1:100, right, where the smaller black hole is 100th of the bigger black hole. Then this would be quite useful. So what we found is the ideal way of discretizing our equations is a new paradigm. It's only about 15-20 years old, called discontinuous Galerkin methods, where imagine if you have a one-dimensional domain. What you do is you split your domain into elements, and within each element you have a spectral basis. Just like the global spectral methods, these have local spectral bases here. And so they are able to sort of adapt to inhomogeneous grids, and they can get high order accuracy within these elements quite easily. The key here is that all the communication that any given element needs is from its nearest neighbor only, right? So this really reduces the communication overhead of this discretization scheme. Many other discretization schemes exist, but they, as you want to go higher order accurate, second order to third order, fourth order, fifth order accuracy, you require as many neighbors to send you information from both sides at every time step. So DG methods are rather unique in this sense. So you can see when we compare them with spectral methods, the clear advantage is they can handle discontinuities. When we compare them with finite difference methods, the main advantage is that these DG methods are still local when we require high order accuracy, right? And same thing with finite volume methods, although these are more used in engineering simulations than GR simulations. Next thing that we did was implement local time stepping, right? So this is our full simulation domain, and you can see the source is right in the center, and out here is pretty much just vacuum, right? So being able to do long time steps in this region, you can imagine how much more efficiency we will add to these simulations, right? And finally, the third critical paradigm shift was from the way we parallelize our calculations. We go from a MPI domain-based parallelization where what often happens is you have many cores performing calculations, but most cores stay waiting for the slowest of them to finish its own assigned tasks, right? We move to something called a task-based parallelization scheme, where the shape of the domain and geometry are entirely abstracted out. You list the calculations you want to do at every time step. You create a dependency graph of these calculations, and then the scheduler simply passes through the dependency graphs using any and all available cores. So in this picture, what will happen is once this core number 4 has finished its task, it will start helping core number 3 here. And same thing will be true for this core and this core. As these three finish their tasks, they will all help this poor guy finish all of its work. Okay, so these three paradigms we have implemented in a brand new open source code, this called Spectre. And so Spectre is still currently under development, and this is a sneak peek into some results. This figure here shows two-dimensional Kelvin-Helmholtz instability with a high density fluid in the middle moving to the right with a magnetic field on the right, and a low density fluid moving to the left here. And these pictures show basically 6 different versions of Spectre with 6 different high resolution shock capturing schemes. And the point of this figure was to show that these two schemes work better than most of the others. The point I'm trying to make here is that Spectre is finally able to do full-scale simulations, although not yet handle black holes in a dynamical situation yet, which is something that we are working on, right? So again, this is an important figure to remember. So remember, I talked about how these codes are not the most efficient. So if you look at the current generation numerical relativity codes, if you try to solve the same problem with more and more cores available to you, what you find is after you have reached about 100 cores, the efficiency of the code does not increase anymore. In fact, you don't get any more speed up by adding more cores to solve that problem, right? But with Spectre, you get strong scaling all the way up to about 500,000 cores that we have tested it on. And this is simply out of the box. We took Spectre from our laptop onto Blue Waters machine in the US. And we didn't have to do any sort of fine tuning to get this excellent strong scaling that we have seen here. And most of the credit here goes to the combination of task-based parallelism and DG methods, right? So just to summarize, numerical simulations of black hole binaries are key to detecting and extracting scientific information from binary black hole observations. And the current generation of codes have done a lot, but they are already at their fundamental limitations. And going forward, as we go towards more accurate detectors, maybe the next versions of LIGO Virgo detectors, or even third generation detectors, we will need to think differently. And that's how Spectre was born. So Spectre is open source from the beginning. It's also radically different computational astrophysics code. It's designed to solve any astrophysics or just physics problem that you may want, not just numerical relativity. And the key benefits of Spectre are these three, which I already discussed and illustrated. And finally, the status of Spectre is such that most of the equations have been implemented. Some of the technical aspects of handling black holes still need fine tuning. So that's sort of the way stage that we are at. And this is the GitHub page for Spectre that I welcome you all to look at and possibly explore. And Spectre has extensive documentation, so please have a look, play around, and if you have any questions, feel free to contact me. Okay. With that, thank you for listening.
Thanks very much for a really interesting talk. We have time for just one question, and can I see whether there's another hand raised just to make sure some, yeah, there's a hand raised there. So, yeah, just, sorry, I'm just trying to be fair to all questions.
Hi Prayush, thanks for the nice talk. So I think I missed this local time stepping thing. So how, like in the slide, I felt like it's more like an adaptive mesh refinement, but like is it a adaptive in the evolution process or?
So is your question about is it adaptive or passive or
like how is it different? Like how is it different from like adaptive mesh refinement, which is like in the spatial grid? I thought like
so adaptive mesh refinement is about how many grid points you place where. But once you have made your grid, you do your evolution, right? Forget about black holes. Any system, anytime you want to simulate something, typically you do a global time step. You evolve the entire domains in sync, forward in time, right? That's not what is happening here. So what is happening is, so this is a 1 plus 1D projection of the 3 plus 1D problem, right, in this graph. So this is a smaller black hole, this is the bigger black hole. And the smaller black holes will have smaller length scales and therefore smaller time scales. So we need to take the shortest time steps when evolving this region, right? So this is the length of the time step taken. In the time it takes, we take 2 time steps here. We take only 1 time step near the black holes, near the bigger black hole. And in the time we take 4 time steps near the smaller black hole. and 2 time steps near the bigger black hole, we take only 1 time step in the exterior region, in this sort of the emptiness that surrounds the source at the middle. And then the obvious question is, how can we do that, right? We can do that because, technically we do that because, sorry, let me rephrase that. So the way we do that is, suppose you're standing here and you want to take this next time step here, right? You need information from left neighbor and right neighbor. So right neighbor and left neighbor, we take the space-time data from the past, which is not shown in this figure, and we extrapolate forward in time, just for a little bit. And that's how we get information from this neighbor into this cell, and this neighbor into this cell, and then we take this time step. Now when we are here, we want to take the next time step, we already have data here from this neighbor. But we still need to extrapolate from this neighbor to get information and take this time step, and so on. So typically we have factors of 2 reduction of time steps. We don't have arbitrary reduction, it's like half, 1/4, 1/8, and so on. And we have been able to manage about a factor of 1/16 stably.
Nice. Okay, thanks.
So in the interest of time, okay, there's, I think, one question there. And several questions. It's going to, I think we need another session just for questions.
We can just eat less.
No, it was really nice. I have questions as well, but I'm going to keep them aside. Yeah, Anjan.
Yeah, thank you for this very interesting talk. I just have one small curious question. How you implement this modified gravity in your numerical relativity? So usually in cosmology, we do, when you do the perturbation calculation like effective field theory, or in CMB, we use the 2 gravitational potential and try to see that difference. So in here, how you implement it? Means you implement it perturbatively, or some effective field theory approach?
Right. So let me start with prefacing that when we implement just normal gravity, normal GR, there is no perturbatory treatment at any level whatsoever. It's implemented in full nonlinearity. Now, if we want to do that for any alternative theory of gravity, the steps would be first to prove that you can write down an initial boundary value problem for that, right? Given some initial data and data at the boundary of space. Is it a well-posed problem to do an evolution in that theory? And this question in itself, I am not aware of any other theory of gravity where it has been already addressed. So that is sort of step 0. Then, well, you can be reckless and forget that and assume that it has a well-posed IBVP, Cauchy problem, well-posed Cauchy problem. And what you can do is sort of start with some form of initial data that you can come up in that theory, and simultaneously write down that theory's evolution equations, write down that theory's sort of boundary conditions, which would be sort of outgoing transparent boundary conditions. And these 3 pieces are essentially what you need. You just code these equations up in Spectre, and Spectre would take care of the rest of the technical aspects, the numerical discretization, the evolution, the grids and everything. The code will take care of. But roughly that would be the roadmap of how you would do what you're asking.
But just one small thing, like when you put this evolution equation, so you put the whole modified gravity evolution equation, or put it on the GR and then you put it perturbatively like that?
That's up to you, right?
Okay, fine. That the Spectre.
You can do either,
okay.
But preferably whole modified gravity equations. But what has been done in the recent past is people have taken some modified theories which have a smooth limit to GR. Then they have taken a small parameter deviation from GR and sort of calculated the first order evolution equations for the extra degrees of freedom in that theory. And using GR's equation as background, evolved only those extra parameters to sort of get a first order approximate solution in that theory, but that is not numerical relativity in the strict sense.
Okay, so I think in the interest of time, please do ask the speakers questions later, but I think we'll wrap up this session.